I talked a little bit about the nth partial sum in the last video when I was talking about a finite series. Basically, if I was taking a sum of a sequence, just the first 5 or 10 or whatever terms, we sometimes call that a partial sum. And so, I wanted to look a little bit more about the nth partial sums of a sequence and the pattern that happens when I start adding consecutive terms of a particular sequence. Because sometimes there can be interesting parallels between a sequence and its respective series. And so, just to sort of define the partial sums, and sorry that this diagram is a little bit blurry, but it says for the sequence A1, A2, A3, A4, and so on, the partial sums are defined to be S1 is the sum of the first term. S2 is the sum of the first 2 terms, S3, the sum of the first 3 terms, and so on. Basically, S sub n always represents the sum of the first n terms. And we refer to these as the first, second, third partial sums, and so on, where the generic S sub n is the nth partial sum of those things. And what's interesting is a lot of times if we have a formula for A sub n, sometimes we can actually find, well, what is S sub n for that, the generic sum of the sequence. And there can be some interesting connections between sequences and series. Something that if you ever have to take Calc 2, a second semester calculus course usually goes into that quite a bit in more detail, and there's a lot of interesting stuff in there. But we refer to that sort of sequence. This basically, notice that starting to add them up forms a new sequence, and we could figure out the sequence of the partial sums for a sequence itself. So let's actually do an example. It says find the first 5 terms of A sub n is equal to 1 over 2 to the n, then find the first 5 partial sums, and let's see if we can find any connections here. So let's go ahead and start by listing the terms of the sequence. So we have our formula, so we can find A1, A2, A3, A4, and A5. So A1 would just be 1 over 2 to the n power, which is 1/2. A2 would be 1 over 2 squared, which would be 1/4, and so on. So basically just elaborate just as I would have functioned by plugging in 1, 2, 3, 4, and 5 in for n. Then the next one would be 1 over 2 to the third, which is 1/8. Also notice that this is a geometric sequence because it is getting smaller by a factor of 1/2. Like I'm multiplying by 1/2. Each time it's being cut in half. It's not written in the format of a generic geometric sequence, but if I was to translate this back to geometric sequence using the formula, I would have, well, the first term is 1/2, the common ratio is 1/2 to the n minus 1. And actually notice that what I just wrote, which would be using the formula for the geometric sequence formula. Did I call this arithmetic sequence a minute ago? If I did, I mean it's geometric. Sorry, I don't remember if I did. If I misspoke, I sometimes mix them up just because it's an accident, but it's geometric. And so if I use the geometric series sequence formula, I would get this. Also, sometimes I mix up sequence and series because, again, as I said before, they're so similar. It's never intentional. It's just brain not using exactly the right word. But basically, first term is A, common ratio is R, AR to the n minus 1 is the formula for a geometric sequence. And anyways, this is actually, if I simplify this algebraically, this would leave me with 1/2 to the n, and that could be represented as 1 over 2 to the n. So these are the same thing. Anyways, sometimes, a geometric sequence might just look like a different exponential function in the denominator. But anyways, let's continue with finding the first 5 terms. Next would be 1 over 2 to the 4th, which would be 1 over 16, and then 1 over 2 to the 5th would be 1 over 32. So anyways, we get these particular 5 terms to start with. Here's our sequence. So now let's look at the partial sum. So S1, S2, S3, S4, and S5. And again, that would just represent the sum of all of the terms up until that point. And S1 is always equal to just the first term because it's the sum of the first 1 terms. Of course, it's just 1/2. And then looking at S2, that would just be the sum of the first 2 terms. So 1/2 plus 1/4. And, doing a little bit of fraction math here, we would need a common denominator to add them together. So this would be 2/4. 2/4 plus 1/4 is 3/4. And that would be our second partial sum. Our third partial sum would be the sum of the first 3 terms. So, adding all 3 of those together. But, you know, another shortcut that you could do for the third partial sum is, since the second partial sum I've already added up the first two terms, I could just take, instead of doing that, I could take S2 plus A3, because, you know, it's sort of a simplified process. And basically, you know, the nth partial sum is always equal to the nth term plus the previous nth partial sum. This would be a generic formula for the nth partial sum, because, you know, if you're solving them sequentially as I'm doing, basically you just need to add the next term to it. But like in this case, or obviously you could just add up the first three terms as the chart suggests: 1/2 plus 1/4 plus 1/8. But, you know, my whole point was this I've already done if I'm examining the sequence. But that would just be 3/4 plus 1/8. And to have a common denominator there, I would need 8. So this would be 6/8 plus 1/8. That would give me 7/8 for my next one. And then, you know, for S4, and so this was sort of the shortcut as I was saying, I would just replace that partial sum with what I've already figured it out to be, 3/4. And like to look at then the fourth partial sum, well, that's just the sum of the first three terms, which is 7/8, plus the fourth term, 1/16. Because again, this one should be the sum of all four of those, and I already know those three are 7/8. So 7/8 plus 1/16. Again, notice there's a kind of a pattern here to how to figure these fractions out. To make a common denominator, I multiply the first one by 2. This would give me 14/16 plus 1/16, which would be 15/16. And basically, the one of the points that I wanted to illustrate here is that when I'm looking at the sequence of the partial sums, sometimes that forms a new sequence, or there's a pattern which occurs that I could use to sort of analyze this process. And here, I could even predict the next term. Notice that the denominator is exactly the same as the denominator for the original term, right? Like here was 1/2, then 1/4, 3/4, 1/8 to 7/8, 1/16 to 15/16. Notice that the nth partial sum is actually just the reverse fraction if you subtract from 1, right? This one would be 1/16. This one is the exact opposite, 15/16, the other side of the pi. And like, so if I was guessing, well, what would the next one be? If this is 1/32, my guess would this be with 31/32. It's basically one less than the denominator in each case. And let's just go ahead and see if that works. Well, I'm going to take the sum of the first four plus the fifth term to find the fifth partial sum. And again, in order to add those up, this would be 30/32 plus 1/32 would be 31/32. And I can quickly see that, yes, that pattern holds. And, you know, kind of trying to sum all these ideas back together, no pun intended, the original sequence was 1/2 to the n power. It was a geometric sequence. When I started to add it up into the form of a series, that actually became, the denominator stayed consistent, but what happened to the numerator in each of those terms was it was one less than the denominator. And actually, I could write that by doing 2n minus 1, because I already know that numerator, I already know the denominator is 2 to the n, and the top is just 1 less than that. And basically, this sort of connection is kind of interesting, and there's certain ways to find these sorts of things. It's something that is not often so easy as it was in this one. I wouldn't even say this one was easy, but just the point of going into all this is that looking at the sum of a series can have some interesting implications. And in the next video, I want to talk a little bit about Zeno's paradox and kind of get back into this idea of infinite series a little bit further.